Section 5.5 looks at another important kind of trigonometric function, the inverse trig functions. Now, if you remember from an algebra course, if you have a function f of inverse, it's called the inverse function. That -1 and the exponent to indicate that it's an inverse. And what that means is that if f of x is equal to y, f inverse of y equals x. Now, what has to happen, f must be a one-to-one function. And the test that you usually see for this in algebra textbooks a horizontal line test. So let's look at a trig function and see how we can work out this notion of an inverse trig function. So if the trig function takes in a real number, spits out some other real number, some coordinate on the unit circle, I'm curious as to how I can reverse that process. So let's try the sine graph, and I'll put it on both sides of the axis here, just so we can see how the whole thing behaves. 3 pi over 2, 2 pi, negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. And there's, of course, our 1 and negative 1, so we know the amplitude. Now, we know that the sign is 0 there, 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 but also tracing the unit circle the other direction, we would get the sign is going to be 0 there and there. We're at positive 1 here, negative 1 here. So there's our usual. And then we're going to get the opposite behavior over here. Let's just clean that up. So if I try to apply a horizontal line test here, I'm going to get a problem. This is not one-to-one. So I need to restrict this to a section of the graph that is one-to-one. And so what I'll choose to make life easy so we will restrict domain negative pi over 2 to pi over 2, which means I'm only going to have that chunk of the graph, which you see does intersect the blue line only once, and so that's going to be a portion of the domain of the sine function where the sine is one-to-one, where the function is one-to-one, so an inverse can exist. So if I've got sine x restricted to negative pi over 2 to pi over 2, well, suppose I wanted to find sine inverse of 1/2. Again, this superscript of a negative 1 is going to indicate the inverse, or you'll sometimes see this written as arc sine of 1/2. The arc prefix and the negative 1 as a superscript indicate the same thing. Your calculator might have this, it might have this. But what this is asking, suppose I said this was equal to some value x. Well, what this is really saying is sine of x has to equal 1/2. So if I want to compute the arc sine or the inverse sine of 1/2, I'm asking sine of what value is equal to 1/2. Now we know the sine is measuring on our good old unit circle. It's measuring y coordinates. So if there's 1/2, it's really saying how far did I have to go to get to here? But it could also be saying how far did I have to go to get to here? We're going to get multiple results. Or really, if I wanted to keep going, how far did I have to go to get to here, right? We've got lots and lots of results for the sine of 1/2, which is why this domain is so important. We're restricting ourselves to something that's either in the first or fourth quadrant. So when is that positive 1/2? Only for that arc length right there. And if we review our tables from earlier lessons, we know this is true. 1x is pi over 6. And therefore, the inverse sine of 1/2 is pi over 6. Now these two functions should be able to be composed. So if I had sine inverse of sine of pi over 6, this is sine inverse of 1/2, which we have from the last page. It's pi over 6. There's the pi over 6. There it pops right back out. Now similarly, if I had sine of sine inverse of, say, 0, this is asking sine of what value is equal to 0? Well, 0, right? If we go back to our unit circle, we're between negative pi over 2 and pi over 2. When is the y-coordinate 0? Right there, at the arc length of 0. So we just get sine of 0, which we know is 0. Matches up there and there. We can also look at the sketch. So I'm going to restrict myself to the negative pi over 2 to pi over 2, which gives me these 3 nice points for my sine graph. So in the red I've got y equals sine x, and in blue I'd like to graph y sine inverse x. Now again, if you recall from any kind of a college algebra course, if you need the graph of an inverse function, we should be able to find it by flipping the graph over the line y equals x. So if I look and say, okay, well there's the line y equals x. That's a pretty inaccurate line. Let's see if I can make that a little bit better. Should still be starting in there. Yeah, I'll skip that. It's drawn not quite to scale. But we should still be able to get the premise by going and looking to see, okay, well along here, I'm going to be curving down. So over here, I should be curving up. And to make these things match, previously I had an input of pi over 2, which gave me an output of 1. Now I'm looking for an input of 1 and an output of pi over 2. And similarly, for an input of negative 1 and an output of negative pi over 2, I'm going to get a graph that looks something like that. And again, as usual, my art skills are not quite up to par, so check your text for a little bit more of a detailed drawing. But I could extend this idea not just for an arc sine or an inverse sine, but I could define the inverse cosine, the inverse tangent, the inverse secant, the inverse cotangent, and the inverse cosecant. And for every single one of these, you're going to need to restrict the domain to make it 1 to 1. For the cosine, we can restrict it to 0 to pi. For the tangent, we can go from negative pi over 2 to pi over 2. But notice, these are parentheses, not brackets. I cannot include the endpoints for the tangent because we saw in the last section the graph of the tangent has vertical asymptotes there. The inverse secant gets even weirder because I actually have to break it up into two pieces. Zero to pi over 2, but we had an asymptote at pi over 2, so I can't include that. Now I actually have to take the union of that with pi to 3 pi over 2. The cotangent has similar behavior to the tangent, but because it's going to follow the same pattern as the cosine, the same way tangent follows the same pattern as the sine, we're going to get a domain from 0 to pi there. And the cosecant is going to follow along similarly to the secant, 0 to pi over 2, and pi to 3 pi over 2. So your text has a number of activities that I recommend you look at, where you can see the pictures of the graphs, but the same general notion applies no matter which one of these you're trying to compute. If I wanted to find tangent inverse of the square root of 3, I'm asking for the tangent of what to be square root of 3. And again, from the tables that we derived in the past, pi over 3. So, make sure you're very familiar with those basic numbers that we've been using over and over again. The values in the first quadrant for the sine and cosine and the tangent. When you need to compute the inverse function values for these, we want to refer back to those tables because this is the kind of question we're usually asking. If I want to know what is the inverse tangent of square root of 3, I'm asking the tangent of what number within the domain of tangent, or within the domain rather the inverse tangent, gives me square root of 3.